Okay. So for this, maybe let's go back a bit. Okay, so for last time, we learned the Ampere's law. Ampere's law. So actually, it's about a line integral for the magnetic field will be equals to the total current it enclosed by this Ampere loop, and the direction follows the right hand rule. So let's continue. For this one, two circular arc have radii A and B. So the longest one is A, this one is B. Subtend an angle theta equals 74 degree carrying current I, and share the same center of curvature P. So share the same center P, this point. And what are the magnitude and direction into or out of the page of the net magnetic field at P? So we want to calculate the magnetic field at this point. And the current is rotating clockwise. Okay. So actually, this is really simple. It's very simple. So this loop can be separated into four segments: A, B, C, D, C, D, something like this. So for AB, because P is on the same line of AB, so this segment will not contribute any magnetic field at point P, and so as CD, So the only only segment will generate magnetic field at point P is BC and DA. So the magnetic field will be equals to mu0 I theta 2 pi b 2 pi b minus mu h. Mu0 I also theta 2 pi a. Because for this segment, using the right-hand rule, at point P will be out of the page, and for BC will be into the page, and for the other term they are the same. So the magnetic field is inverse proportional to the radius. So B is smaller, so that term will be larger, and so we write it like this, and we can factor it out. Mu0 I theta 2 pi 1 over B minus 1 over A, and then we substitute all the values. 4 pi times 10 to minus 7 times 0.411 times 74 degree. We need to convert it into radius, so it will be something like 74 over 180 times pi over 2 pi, and B is 0.107 minus 0.135, something like this, and then we can know that It is actually 1.02 times 10 to minus 7t, and the direction should be out of the page. Out of the page, because this one is larger, this one is larger, and this one is smaller. That one point into the page, this one point out of the page. So cancel some of it, part of it is cancelled, and the overall magnetic field is out of the page. So this is pretty easy. Pretty easy. Any questions?不用假设。Okay, so this segment point out of the page, that segment into the page, and this one should be larger. There's something like that. Or actually, you can assume something like mu 0 I theta over 2 pi a minus mu 0 I theta over 2 pi b, and then the positive direction will be into the page, and finally you get a negative answer. Then because if you consider that term is positive, I mean the first term is positive, then this one positive, so this is out of the page, and then the answer is positive, so it is really out of the page. If you assume into the page is positive, then you get a negative answer, and then the finally it is out of the page. Okay, next one. So a long circular pipe, which is this one, So this is a pipe with outside radius R equals 2.6 centimeter, carry a uniform distributed current. So a current is distributed on the light blue area. I is 8 milliampere into the page. A wire runs parallel to the pipe, which means this one, a wire runs parallel to the pipe at the distance of 3R from center to center. Find the magnitude and direction of the current in the wire such that the net magnetic field at point P has the same magnitude as the net magnetic field at the center of the pipe, but it is in the opposite direction. So which means we need to have magnetic field at point P, which has magnetic field which has the same magnitude but opposite direction. Compare with the center of the pipe at this point. Okay, so we may call this point C. Okay. So actually, first we need to calculate BC. BC would be equals to mu mu 0 I W. IW is the current at this wire, and actually we need to calculate IW, and 2 pi 3 R 3 R 3 R. So for this term, we assume the wire has a current IW, so it will generate a magnetic field at point C. So the distance between the wire and point C is 3R, so we have 3R here. And actually, the magnetic field contributed by this pipe would be zero. IW means the I of this, the current of this wire. We denote it IW. And pointing. Okay. So first of all, we assume IW is into the page. So this magnetic field is pointing to the left. IW into the page. So using the right-hand group, this one pointing to the left. So at point P, we need to calculate that the magnetic field contributed by the wire will be mu 0 IW 2 pi R. The distance is this one. Okay, so this one is the magnetic field contributed by the wire, and for the pipe, we can know that it is actually mu 0 I over 2 pi R, 2 pi 2 R. Actually, we use the Ampere's law. We assume a Ampere loop like this, and then we can know that the magnetic field at point P contributed by this pipe would be something like this. It's something like all the current is condensed at the center of the circle, something like that. We can simply know that. Something like what you did for the Gauss law. Okay, so we do some simplification. So we know that mu 0 IW 2 pi R minus mu 0 I 4 pi R. Actually, this one also points to the left. But for the question, we hope actually we hope BC equals minus BP. Actually, we hope it will like this. So I open a new page. So we can write it like mu0 IW over 6 pi r equals mu0 I 4 pi r minus mu0 IW 2 pi r. So we move the term to the left. Then we'll have mu0 IW 2/3 pi r equals mu0 I 4 pi r. Then we just cancel the common factor. Then we know that IW equals 3/8 I. Actually, it is 8. So IW should be 3 milli 8. So this one is positive, and in the previous, at the beginning, we assume IW is into the page, so if this is positive, so IW is actually into the page. Okay, any questions? C 点0，就是 the current for this pipe is into the page. Is into the page. So so you can imagine well, maybe I draw it here. So the pipe is something like this. Okay, something like this. You can imagine something like this. I have an ambient loop here. So there's no enclosed current. So for this one, E dot ds will be 0. And you further decrease the radius of this ambient loop until here, then it will also be 0. Or you can imagine that for another point of view, you have a D, you have ds here. So for this one, this is into the page. So using the right hand rule, the magnetic field will be point to this direction. And actually, you have another part here for this ds prime, ds prime for this part. This one will point to that side, then they will be cancelled. So no matter how you think, the pipe will contribute zero magnetic field at this point. But for outer, it is not actually. I'm not sure whether it's actually. Yes, it should be zero. It should be zero. Yeah, they are symmetric. So within the pi, the magnetic field is zero. Okay. Any other questions? Okay, so we have finished chapter 29.